All right. So what did we talk about last time? Last time we talked a bunch about, let's see, we talked about local stability stuff. And this is sort of this idea that if you have a nonlinear system, you can linearize it about something and check the eigenvalues of that, that Jacobian matrix, and those will tell you about local stability. And basically, in continuous time, you're checking that the real parts are negative. And in discrete time, you're checking that the modulus is less than 1, right? So it's a contraction. So that's kind of that idea. And that's super useful. You use that all the time. And it's, as someone mentioned last time, it's kind of closely related to these sort of old school CISO control ideas where you're kind of trying to shape the eigenvalues. And then we talked about Taylor integration, which is the very oldest, most ancient form of ODE integration, where you just kind of take the Taylor expansion and ride along the Taylor expansion for a delta t to get your next time step. And we talked about how that sort of gets terrible past about second or third order because you got to compute these big tensors. We don't like doing that. There's more to say about that story. These have gotten somewhat popular again for a weird reason. Basically, in the modern era of automatic differentiation, it turns out you can actually compute those tensor terms somewhat efficiently. So people have gotten into these again with automatic differentiation tools, but still not very, very popular. And then the last thing we talked about, right, was this idea of Runge-Kutta methods. And these are the bread and butter thing that you'll see all the time that are most common. And essentially the idea there is we can do the Taylor, we can basically get the Taylor polynomial out by, rather than Taylor expanding, by taking a bunch of sample evaluations and essentially fitting a polynomial through the samples, right? So it's essentially like fitting a spline through a bunch of sample points, right? And that ends up being a lot easier to do than taking a high order Taylor expansion. Yep.
So maybe so these like new methods of Taylor integration, why are they better?
They're not better. They're like, they literally do the same thing, right? Okay. The reason they've gotten popular again is that we have AD tools that can compute these higher derivative things. So specifically what you actually need to compute these is not the tensors, right? You need the tensor vector product, which is what all these AD tools are all about, right? That's literally what like PyTorch and TensorFlow are built for. Yeah. So if you have a good AD implementation that can compute higher order tensor vector products like this efficiently, which is not easy to do, right? Like the PyTorch stuff only goes to like second derivatives, basically, with those tensor vector product things. These are sometimes called pullbacks, right? Or whatever. But anyway, so if you have a like fancy AD thing that can do like fourth, fifth, sixth order, tensor vector product things efficiently, then this gets actually maybe plausibly okay to do. And the reason you might want to do this is what it actually gets you now is you have like a sixth order, say, or if you did fourth order integration, say you'd have a fourth order Taylor expansion for the deltas about your solution. And this lets you, for example, propagate like an error distribution to high order along the trajectory. So it lets you propagate, like efficiently propagate, say, like moments of a distribution or a noise, distribution or whatever, or some error metric to high order, right? So basically, like, essentially, if you can do this, you can almost propagate like a probability distribution around your trajectory almost for free by doing it this way, if you've already got that tensor expansion, right? Does that make sense? Yeah. Like probably everyone has seen like this idea of like propagating a Gaussian through a linear dynamics thing using the Jacobians, right? That's not very accurate. With this Taylor thing, basically you can compute this like high order Taylor expansion and propagate the distribution to high order, right? That's kind of the idea. Does that make sense? So that's why they're kind of interesting, but they hinge critically on having a very efficient, like really good automatic differentiation capability that can go to high order, which the stock ones don't. So you need a very fancy AD toolbox, which there are. People have done this. This is like a research thing that's been kind of interesting in the last few years. Okay, so that is why. Yeah. It's a sort of long digression. You can yeah, that's kind of it. So if you wanted to do a similar thing with ODE 45, like propagate an error distribution to high order, probably what you would end up doing is like essentially a Monte Carlo or unsended transform thing, where you could just sample points and propagate all the sample points, right? Like that'd be the alternative thing, which fine, but you kind of give up any sort of guarantees about anything when you do that. or it's harder to get guarantees. Whereas these Taylor things, you can basically say exactly what's going on up to whatever order in the distribution in the moments. Yeah.
So like all the arcane methods, you said that they sort of implicitly fit a polynomial to
Yeah.
the delta. What if you explicitly fit the polynomial? Is that
I mean,
something-
that's how you derive the arcane method. Like you literally write down the polynomial and then you match it up with like evaluations of f and say, okay, I want to match fit the polynomial with. I mean, that's how they're derived.
Well, if we have the explicit polynomial, can't you do the same sort of propagation that you do with Taylor expansion?
I mean, you basically what these are all doing is interpolating the solution with a polynomial, essentially with a spline, right?
Yeah.
So you pick an order of spline you like. You can get the polynomial coefficients either with a Taylor expansion or with a bunch of samples you can fit to the polynomial, right? Like
No, but I mean like for the error propagation stuff.
Mm.
Because if you have the spline that you fit in, can't you?
Yeah,
fit it
so
the same way?
it's a little different. So what's going on here, this is giving you this polynomial in time is what when we say, fit to the solution with a polynomial, we're talking about x of t. So it's a polynomial in t. Does that make sense?
Yeah.
And when we talk about this error stuff, we're talking about a polynomial expansion in delta x.
Oh.
Does that make sense? So when we say spline, we're talking about x of t. So it's polynomial coefficients on the t. So it's a 1D function, right? It's a maps from R to Rn, right? Where R is time, right? Whereas this error thing, we're talking about a mapping from like delta x in Rn, right, to delta x at the next time step Rn, right? So this is for the linear case, that's a matrix. If you want to do that to high orders, right, in the Taylor expansion in delta x, it ends up being a high order tensor, high rank tensor, right? Which is kind of what we saw last time when we did this Taylor integrator thing, right? Which is messy and hard to do and expensive and blah, blah, blah. Does that make sense?
Yeah.
So yeah, it's expansion in time versus expansion in like the spatial dimension. Yeah. Okay, cool. Anybody else? All good? I mean, I think they're literally called Taylor integrators. If you Google that, you will find stuff on this. Basically, they're using the fact that you have the high order Taylor expansion in the state space to like propagate. Essentially, what you can do now is, right, so when we talk about linearly propagating like a Gaussian, what you're really doing is propagating the covariance, right? And so now if you have higher order expansion, you can propagate higher moments of the distribution, right? Exactly. And that's so you can go to fourth, fifth, sixth, whatever order in the moments of the distribution. That was a long sort of like random. You can easily distract me is the the moral of the story. So feel free anytime. It's a grad class. We don't have, we're just, this is all for fun, it's whatever. Yeah, if anyone's like has, like a burning desire to like learn any particularly interesting topics in like dynamics, or simulation or whatever that vaguely falls under the topic of this course, just let me know. You can talk about kind of whatever you want. It's very open-ended. I have some things that I think are worth knowing about that I'm telling you. That's basically, what it is. If there's some things you want to know, let me know. We can do that. So yeah, so we're going to talk briefly today about higher order Runge-Kutta methods and like how that whole thing works, and basically what the state of the art sort of stuff that you're used to using, maybe like ODE 45 and stuff like that, like what they're actually doing under the hood and how you get them. We're not going to derive them because it's just messy. So I'll show you like how you derive it, but we won't actually go through the pain. And then like just a little bit more on that, like what those things do. And then we're going to talk a bit about sort of like this idea last time where we saw how like the Runge-Kutta methods, the explicit ones and the Taylor ones, they still blew up when we put high damping in, but the implicit midpoint was like rock solid and conserved energies. We're going to poke at that a little bit more today and kind of tell you a little bit more of that story. So the key word there is stiffness. Has anyone heard of a stiff ODE before? This is a weird thing. Heard about this a little bit? Does anyone have a definition of that or know what it means? So if it's stiff, it means it's hard to integrate with an ODE solver. But there's actually no like rigorous mathematical definition of this. It's basically one of these like just engineering lore things, right? Like if a thing is hard to solve with an ODE solver, it's called a stiff ODE. And it vaguely corresponds to like high stiffness in the like spring, kind of sense, which implies there's like high frequency stuff going on, which means you have to take tiny time steps, right? That kind of idea. But it's not exactly that. And there isn't actually a rigorous mathematical definition, which is sort of funny. So stiffness and stability of Runge-Kutta methods. And this will be kind of the end of our discussion on these things, which are kind of the classic, if you just have an ODE you got to solve and you go to your computer, like this is probably what you're going to do. And probably you've done this already with something like ODE 45 or whatever, if you've ever done this before, right? Okay, so like basically today will be what's up with ODE 45? How do you get that thing? And what is it doing? And where is it going to break? That's sort of what we're going to talk about. Okay, so this whole story. Yeah.
Hey, Zach, are you supposed to be sharing your screen?
Oh, I am not sharing the screen. Apologies. Pretty terrible. Thanks for speaking up. Can you see that now?
Yeah, perfect.
Okay, cool. Thanks for, letting me know. Okay. Otherwise, we would have had a very terrible YouTube video for this section. Okay. Higher order Runge-Kutta methods. What's going on with that? So, I mean, this is not a surprise. Basically, we saw how to do second order yesterday or Tuesday. And basically, you take a second order Taylor expansion of the solution in time, right? X of t. And you fit the polynomial coefficients. So it matches the Taylor distribution or Taylor expansion. Second order. And you can keep doing that. And, it just gets messy at a higher order, right? I'm trying to talk and write, and it's tricky. Okay, so like basically, if you want to do this in general for arbitrary order, you would sort of first choose a number of stages that you are willing to live with. Choose if you want to be, sort of like implicit or explicit. Write down the integrator step with undetermined coefficients, like undetermined weights, right, on the Fs. Write down the Taylor expansion. And then basically, then you choose the weights in the Runge-Kutta step to match the Taylor expansion. That's it. But yeah, as you can imagine, like these steps get messy, in particular, like 4 and 5, right? Writing down these Taylor expansions with all those tensor terms and everything can get extremely messy. Past about 4th order, which is like sort of the pain tolerance that people had back in the day for this sort of thing. So the classic Runge-Kutta method is the 4th order method, right, that we've all heard about. That was derived like over 100 years ago, by hand. And like basically no one did higher order than that until many decades later when we had computers to help us with this. So that appears to be the pain threshold for, doing it analytically. So another comment on this is you can do this, right? But when you get to this like weight matching step, it turns out that the weight choices are not unique in general, past like the, implicit midpoint, second order 1 step thing. There it's unique. It's got to be a half, right? That's the only thing that matches. But it turns out past there, it's not unique anymore in most cases. And so you can actually choose weights to optimize for other things other than just hitting the order. So you can, for example, choose weights to like try to zero out as many as possible for efficiency to make it cheaper to do. You can try to minimize the next term in the Taylor expansion, the so-called truncation error. You can do all kinds of things, right? To optimize your weight choice in general. So that, okay, so we'll see that now. So the classic, most famous Runge-Kutta method ever is RK4. And it turns out there's actually two RK4s because the weight choices are not unique. So yeah, fourth order with 4 stages. And there's 2 of these, like I said. So the fourth order with 4 stages things, the 4-stage thing, right, as we know, it means like you call F 4 times. So we'll write this down, kind of what this looks like in sort of the generic form, right? So if I were to try to derive one of these, I'd write the following thing down, right? I'd write 4 stages with undetermined coefficients. And specifically, when I say undetermined coefficients, I'm talking about these A's buried inside here. Right, so I'm evaluating F at a bunch of like intermediate points. So this is what like the most generic fourth order RK thing would look like. And this is explicit because in each one of these stages, I'm only using past Fs, right, in the future evaluations. Does that make sense? So if I were to include, all the Fs in all of them, then it would be implicit, right? Because I'm using like future Fs in past F evals, right? And then at the end of this, you kind of compute xk plus 1 by computing like some weighted combination of all these Fs. And we call these Vs. There's something coming on this in a sec. Cool. So that's what it looks like in general. And then the game is, I write this down. I can then Taylor expand this whole mess and like write down the fourth order Taylor expansion of x of t or x equals 1. And then I have to find the A's and B's to make this match the Taylor expansion to fourth order, right? So that's obvious, like it's obvious what to do. It's just really messy. And I don't want to do it because it's going to take like all the rest of class to do it. So we're not going to do that. So the thing that is worth knowing about those, so I call these things A's and B's, right? There's this thing called a butcher tableau. Has anyone heard of this before? Yeah. Okay. So here's what that is. You'll see this if you ever like try to look up a Runge-Kutta method. This is how they're classically specified. Matrix A and vector B called the butcher tableau. So here's what that looks like. This is what you'll see written down. So you'll see something like, make sure I do this right. So we got this sort of thing. Okay, so this is the A's and B's. These C's, which we didn't talk about yet, these are if you have a time varying ODE. So if you have like f of t comma x, these are the times that you evaluate at. We're not going to really see any of those in here, but that does happen, which is why we didn't talk about these yet. Okay, fun question. So we talked about how, like this thing is explicit, and that means that you're only using previous Fs, to evaluate the current F. If it's implicit, it means you can use any Fs at any time, right? But then it's a root finding problem. So looking at this butcher tableau, so you have this matrix A here, and this vector B and this vector C, which we're not going to really use. The matrix A, can you tell me anything about the structure of that matrix if it's explicit versus implicit? So what is it right now for this explicit method? It's lower triangular, right? What if it's implicit? Can be full rank, but like full matrix, right? So yeah, basically you can tell by just looking at the butcher tableau if it's an explicit method that A matrix has to be lower triangular. And that's sort of this causality thing, right? That it's only using past stuff. Cool. Okay, so there are two examples of fourth order. So like I said, these are not unique. In fact, you could derive like an infinite number of possible fourth order methods. There's two famous ones that are like super common. And they are the following things. So we'll write down the butcher tableau things for these. Cool. So this one, and then okay, so this one on the left is the so-called classic RK4. And it's the one you'll find actually, I think both of these are on the Wikipedia page, but this is the one that everyone talks about as classic RK4. And this one is called the 3/8 rule. And it's also super common. I think both of these were in the original Runge-Kutta paper from like 100 years ago or whatever when they were first derived. So talking about how these are non-unique and stuff, anyone have a guess as to like what the sort of motivation was for, so why was this one kind of the classic one that was sort of used originally most? Yeah, so it's basically the goal when they derived that one was to zero out as many of the weights as possible to make it cheaper. So there's less FE-vals, right? So you can see, so that's one of the things you can do. You can try to make A sparse, have lots of zeros, and then it's cheaper. Whereas the 3/8 one actually has lower truncation error. It's actually more accurate. Fun fact. Actually, that's right. Yeah, I mean, it's not actually a big deal, and it's not the sort of thing I would actually worry about in the modern era. But yeah, I think you're right. You basically you're just plugging in fewer things into these guys. But yeah, it's in the noise. I think it's technically fewer flops, but it's not anything that matters with a modern computer. Okay. Okay, so this is like how you do higher order RK methods. This is how you write them down. So actually a lot of the ODE packages will actually take as input a butcher tableau. So you can feed them A and B, and they will like do that Runge-Kutta method for you under the hood. This is like kind of the standard way they're written down. The other thing to mention, so yeah, so we can do fourth order, we can do higher order. This is pretty normal. Fourth order is kind of the standard, like everyone does this sort of thing, right? The other main thing that you should know about is adaptive or variable step Runge-Kutta methods. And this is what ODE 45 is doing. So the idea there is you use a pair of Runge-Kutta methods of different orders. So ODE 45 uses a fourth order and fifth order method together. There's other versions of this, right? So there's just the MATLAB ODE package has ODE 2-3, which is a second and a third order pair. And then there's also, it's pretty common to use 7-8 pair as well. There's a standard one of those as well. That's common in astrodynamics, like in spacecraft and orbit mechanics stuff, because you want really high accuracy and you can take big steps there. But the idea is you can take these two different order integrators and you can take the same step with both of them. And the like high order one should have less error than the lower order one, right? So what you can do is compare the solutions with the two methods. And if the difference between them is big, presumably this means, you know, that the higher order one's giving you a better answer. But if the difference between them is big, that means your step size is probably a little big. Whereas if you, like in the limit of small step sizes, these should all agree, right? For tiny, tiny step size, they all coincide. So the idea is you can use this for error control. So if I take the same step with both, if they disagree by a lot, then I shrink my step size. If they agree by a lot, maybe if, you know, they basically agree almost exactly, then maybe I can make my step size a little bigger. I can afford to take bigger steps. Does that make sense? So you basically do feedback on the error between these guys and use it as a method for adjusting the step size. This lets you do automatic error control. So you don't have to actually pick your H or your delta T. You can let this ODE solver do it for you automatically, and it'll automatically adapt. So if your like solution is, you know, pretty smooth for a while, it can take big steps. If you get into a regime where it's really wiggly, then it'll automatically shrink the step size for you. So that's a cool idea, and that's it. So generally speaking, if you just have F equals MA stuff or whatever, and you go try to solve it with a computer and you use a package, it's going to do this. This is what ODE 45 does. This is what like differential equations.jl does. This is the thing to do. And it's a straightforward idea. There's just, you know, subtlety in implementing it well. There is a cool trick with this. So what you can do is find, so there's famous examples of these pairs of like sort of adjacent orders. The trick is for efficiency, what you want to do is make the times at which you're evaluating the Fs the same for the two orders, so that you're not doing any extra work. Basically, there's like a famous, it's called the Dorman-Prince pair, the 4-5 pair, where basically all of the butcher tableau is the same for both of them. And like the subset of it for the fourth order part is the same. And then the fifth one just has one extra row. So you're recycling all the same F evals to do both. So there's minimal extra work essentially. So basically it means like you get the fourth order solution for free if you are already evaluating the fifth order solution, which is cool. Okay, cool. So that's like, you know, so if you have one of these, like ODE 45, for example, you can almost not think about it. You can basically take your thing, hand it to this thing, and it'll automatically do the adapt. You can specify a tolerance and it'll just figure out the step size for you and like just go and mostly do the right thing. There are some caveats to this. So you kind of always still want to be a little smart and check things and, you know, whatever, but this is as close to like set it and forget it as it gets. And generally what you want to use. Okay, so the last piece of the puzzle. These are still explicit methods, by the way, right? Like all these, you know, 4, 5, 7, 8 pairs. These are explicit Runge-Kutta methods. So what we're going to talk about next, there's still caveats, but in general, that's the first thing to try, right? And if that gets you, and 90% of the time, that'll be fine and get you a decent answer. There are cases where this is going to do poorly, though. So this is the sort of what's coming next, the stiff ODE story, right? So even with one of these adaptive methods, because they're still explicit, they still have some of these stability issues. And so what can happen is on a particularly gnarly ODE, something like ODE 45, you may have seen this if you've done a lot of this, it'll end up having to take tiny time steps and basically bog down and take forever to simulate something. And we can make it do this trivially, like the pendulum example. If I do that, it'll like just totally have to take like, I don't know, multiple kilohertz time steps and do really poorly. So there are situations like this, and this is what we mean by stiff. So you may end up in a situation where the automatic thing like is just going to basically take uber tiny steps and like take forever to solve. And that's kind of really what will happen. Because it's doing this automatic error control thing. So it won't blow up, but it will basically take hours to solve, right? Okay, so here's this story. And then, by the way, this stiff thing happens all the time, though, especially in robotic stuff where you have potentially like, I don't know, if you're doing impedance control with high gains, that'll make it stiff. If you're trying to sort of simulate contact interactions with some kind of spring damper model, like that makes it stiff. This happens a lot. So it's not a rare thing by any means. It's very easy to end up in these situations. Try to talk about it. All right. So the gist of this is, you're going to need to take very small steps. Even if the system is smooth and stable, i.e. the damped pendulum, right? I crank up the damping. It's like the most benign thing you can imagine. Totally stable. It just falls down, but like that's stiff. And you can easily make the integrators blow up and go unstable with that kind of thing. What else is there to say? So yeah, this is often the reason, the origin of the name is this often corresponds to large mechanical stiffness or damping. But not always. Which is why there's sort of a strict mathematical definition of this thing is elusive and kind of hilariously so. Yeah, that. No. No precise definition. So here's how we're going to get at this. We're going to look at a 1D or scalar scalar test problem. Very much like what we were doing before, but this is going to be x dot equals ax, where a is a complex scalar, aka eigenvalue, right? Like this is basically the eigenvalue thing we were looking at before, just one of them, right? Okay, so remember on this thing, just our discussion last time about stability and stuff. Think of this like one of the eigenvalues, right? From a system that we're looking at. System is stable when the real part of A is strictly negative, right? And we know the exact solution here. What's the exact solution? Yeah, x of t is e to the at times x naught. Yeah, cool. Okay, so what we're going to do is we know the exact solution. This is all good. We're going to now try to we're just going to plug this equation into our Runge-Kutta stuff and look at the stability of the discrete time system as a function of like time step or whatever. Okay, so let's do, first we'll do the terrible explicit Euler. Okay, so here it is, xk plus 1 equals xk plus f of xk, which we'll plug in, so h a xk. Right, now I'm going to rearrange this slightly. This sort of, the stuff I'm doing now should be super familiar if you took a like SISO classical linear control theory course. So we're going to move stuff around and write this as 1 plus h a times xk. Cool. So now, what do I need for this thing to be stable? Yeah, this thing here, right? We're in 1D, so this is the eigenvalue, right? This thing has to be modulus less, strictly less than 1, right? Okay, so now, if I think about this in the complex plane, what does this look like in the complex plane? As a shape or whatever. So
Is it a unit circle?
xk plus 1 doesn't need to equal xk.
For stability, you want xk plus 1.
That would be a fixed point. This isn't necessarily a fixed point. It's like if it's stable, this thing would decay to the origin, say, right? Right. So that what we want is for this to be a contraction. We want it to shrink, right, and go towards 0. Yeah, no, that's cool. So this is just saying for this to be stable, for it to be a contraction, right? This guy has to have like modulus or norm less than 1, right, to make xk shrink over time. That's what we're saying, right? Okay, so if I think about what this is geometrically in the complex plane, what does that look like? Norm of a thing less than 1. It's some kind of ball or disc, right, in the plane, and it's centered on -1, right? Cool. So here's what this looks like. I'm going to draw complex plane. Should draw it more this way. So this is the real axis, right? Imaginary axis. And we basically got this thing centered over here. And it's like a big circle. And this is filled in. And this is -1. Okay, so what this is saying is like, this is true whenever HA is inside here, right? That makes sense? So it's a function of both the dynamics. This A comes from the dynamics from the ODE and the time step, right? So this is the only place where this is stable, though. This is kind of the big thing inside this disk. So let's think about that for a sec. So what this is saying, right, is like, okay, maybe, so one thing you can do, right, if you're not in the disk, I can shrink H, and that will potentially put me inside the disk. But let's think about our pendulum from before. What does a system look like, or just a spring mass system, right, an oscillatory system? Where's the eigenvalue for like a spring mass system, just an oscillator? On the imaginary axis, right, on here somewhere, depending on the frequency, right? And I can bring it in by shrinking H, but what this is telling you is an explicit Euler is never stable for a purely oscillatory system. So if I'm on the axis, I can literally never make it stable. It's always going to blow up. Kind of interesting. So this is one of the reasons, one of the many reasons why you should never use explicit Euler. It is literally the most terrible integration method. If I have a tiny, tiny bit of damping, so I'm just inside here, then I can shrink H to bring it into the circle, right? But basically, this thing has a really small region of stability, which means to make it not look stupid, you're going to have to really tiny time step to try to bring it inside here. And if it's like under damped or very little damping, it's basically always going to blow up on you in finite time, right?
So this is also why highly damped.
Yeah. So if it's highly damped, you're over here somewhere, right? And that implies blowing up, right? That's what we saw in the pendulum with the damping. If I make H really tiny, I can potentially bring it over here, right? But yeah, it's not good for any of these things. Basically you're always stuck having to take uber tiny time steps. And even then, like if it's really oscillatory with really low damping, it's gonna blow up. Okay, Euler bad. More of the story of Euler bad. So let's draw now. We'll do the explicit Euler, or the implicit Euler, the one that needs root finding. Let's write that down and see what's going on there. So this one's better in some ways, but still not great. So that one is the same thing, except we evaluate f at xk plus 1, right, at the future time. And that's why it's an implicit thing that needs a root find. But that looks like this. So if I rewrite this one slightly, I'm going to get 1 minus HA xk plus 1 equals xk, right? Moving stuff over. And now I can do some more massaging of this and get xk plus 1 equals 1 over 1 minus HA times xk. And then if I like kind of think about what this means for stability, again, like this guy has to be modulus less than 1, right? And we can write that another way as 1 minus HA greater than, has to be greater than 1, right? Okay, what does that look like in the complex plane? Very similar, but now it's to be outside a circle. And the circle is now centered at +1, right? Okay, so let's write that down or draw that. So that's going to look like the following. So we're like, say here, this is +1, and then stable is everything outside of that. So what's going on now? So this thing is super stable. It's stable for anything oscillatory. It's stable for anything, you know, over here with damping. It also artificially stabilizes a lot of stuff over here that should be unstable, right? Like this stuff's all unstable in real life. This thing, basically, we kind of saw this, right? The implicit Euler took away energy from the system, right, artificially, and added artificial damping. This is showing you that picture, right? So this is saying, like, even a bunch of stuff that should be unstable now gets stabilized because the integrator's adding a bunch of damping. And there's just this little circle over here that's the only unstable part of this guy. So what this is saying, though, like anything that actually is naturally stable will stay stable, but a bunch of new stuff that shouldn't really be stable is going to get stabilized artificially because of damping that's added. Cool. Unstable in there, and then this sort of and word of warning, most of the current like robotic simulators use this. So like Mujoko, Bullet, Dart, they're all using implicit Euler basically, or something close, some variation on this. So they are all, and most of them actually add additional damping on top of this to basically make sure that stupid things don't happen. They use this, and they also like to take big steps, right? Like the simulators like to try to take big time steps because it's more efficient, and your controllers typically, you know, are not running at super high rates. So because of that, in order to make things not blow up and not look stupid, they just add tons of damping to the simulation artificially to make it super damped so that it doesn't blow up. they're trying to make it, basically, they try to make it visually not look stupid and not explode on you. So they use really crap integrators. They try to take big steps and they just add lots of damping to make it not blow up. So this is one of the reasons you'll, like, you basically shouldn't really trust results out of simulators without, like, sanity checking a lot of things and blah, 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 and sim to real gap, et cetera, et cetera. It's a real thing, right? But it comes from stuff like this. Okay, cool. So these are the two Eulers that are kind of bad for different reasons, but kind of opposite badnesses, right? Let's look now at the implicit midpoint one. So same thing again. But we're doing this. Average these guys. Okay, so I'm going to massage this around a little bit. So we can write this as 1 plus 1/2 HA XK. We can do this. Again, same story as before. We need this thing to be modulus less than 1. Okay, this is like a little bit trickier to draw or to figure out what it should look like. So this is what we're going to do. You end up with this condition. So I'll write it this way, and then to kind of see what this should look like. Can anyone see when this is true by looking at this? It's not like, it's a little tricky to see. So this is true whenever the real part, if you look at this if you stare at it for a minute and think about it, hopefully this will become clear. It's true when real part of HA is negative, strictly negative. So plug that in and stare at it for a sec and think about it. Yeah. Hopefully everyone can convince themselves that this is true. Okay, so what this is telling us now, if I go plot this, is that this thing has the same stability region as the original continuous system. It's the left half plane. So that is neat. Basically, this one preserves in some deep sense the stability properties, the qualitative stability properties of the original continuous system. Right? Does that make sense? So this discretized system, independent of H, right? I can make H anything I want. It's going to stay over here. So it might move things around, right? But if it's stable to begin with in continuous time and I discretize it this way, independent of step size, it's still going to stay stable if it's stable, unstable if it's unstable, and oscillatory stuff is fine, right? It's oscillatory stuff stays oscillatory, all good. So this thing has this like preserves structural sort of properties of the continuous system in ways that neither one of these guys up here do, right? These guys are all doing weird things and change, like these guys can change your stability as a function of step size and like stabilize unstable things or make stable things unstable, all kinds of weird crap. This guy never does that, no matter what the step size is. So it's pretty special. Yeah. Because it's super stable. Because it's always stable and it stabilizes a bunch of that other stuff. It basically adds lots of artificial damping and is super stable and doesn't blow up. So people like it because it's not going to blow up. So basically, like you don't want to have to, like, if you're trying to make a simulator for someone to just throw a URDF model in or something and use, you don't want to have the user fiddle around with like step sizes and all this stuff to make it not blow up and look stupid. And if you're trying to run controllers and stuff, you probably are going to have a fixed time step for your controller, right? So you don't necessarily want to have like variable time step adaptive Runge-Kutta stuff. And on stiff systems, like we talked about, the variable adaptive step stuff might have to shrink the time steps really tiny to not do stupid things and blow up. And then it takes forever to simulate, right? And it might bog down in certain situations. So that most of the robotic simulators, like Runge-Kutta, et cetera, they use fixed step sizes. And they want to be able to run at relatively low sample rates. They don't have to run at crazy high sample rates. And they also want it to be just plug and play and just work, right? Without having to fiddle with all these things. This guy gets you pretty close to that because of this stability, right? Like it's basically almost never going to blow up. And I can make sure I'm never in here by like just adding a ton of extra damping. So I basically artificially push things over here and live in that region all the time. So like, yeah, so almost all the simulators you see are using this and adding extra damping on top of it, even in a lot of cases, to make it just super damped so it's gonna be stable and not gonna blow up. Does that make sense? Yeah. All right, and then this thing, super cool, does nice things, preserves energy and stuff. The preserving energy thing we didn't really show yet, that might come later, but it has this really cool like structural sort of like preserves stability properties. Yeah.
Sorry, in your notes, you say that stability is true when real HA is less than 1 or 2 syndrome.
Yeah, sorry. Yes, sorry. So yeah, that, and then ends up being independent of step size and blah, blah, blah. Super cool. So let's see, some terminology. If an integrators, stability region contains the whole left half plane, we call it astable, which A stands for absolute. So this is just saying that if I give it a stable system that's stable in continuous time, the discretized version will be stable, right? That's what this says. So, so this guy's obviously astable. This guy, the implicit Euler, is also astable, right? So it includes the whole left half plane. It doesn't really say anything about what else it might do. So that astable thing is, you'll see a lot of that. That's important. So one fun fact is you can prove that no explicit RK method can be astable. So if you want a stable integrator, you basically have to use an implicit RK method. It's actually not hard to prove this. It basically comes down to, if you notice, so it turns out, like this kind of showed up here, the implicit ones all end up with a rational polynomial here. Like as in they get stuff on the downstairs, whereas the explicit ones just have polynomials. And you can prove that basically because this guy has a denominator, this rational form, that can be astable because of the rational form it takes. Whereas this guy, these guys are all just polynomial, and you can't have a plain polynomial like do this. So that's interesting. So what this kind of is telling you, right, is like, if you use an explicit Runge-Kutta method, like, and you give it a stable, relatively benign stable system, it will blow up some as a function of step size somewhere, right? So you can use the adaptive stuff to like adjust the step size automatically to do error control, but if you give it a nasty stiff system, it might have to just slam the step size all the way down to like almost 0 and take uber tiny steps and then bog down. So that ODE 45 can do this, right, et cetera. So if you have a gnarly system that's hard, stiff, et cetera, you probably want to use an implicit Runge-Kutta method, like this guy or whatever. Actually, either one of these, right? These are both stable. The midpoint is better, but yeah, that. What else? Oh yeah, the other fun thing, this is just an aside, is you can write the stability condition. So all the stuff we just derived, you can generalize it. And you can actually write it in terms of the Butcher-Tableau stuff. So it looks like this. This is sort of nasty, but there is just like, you can just drive this like very generic. Okay, so that's it. This E thing is a vector of all ones, which is a common thing in optimization lingo. And then Z is a complex number, which is a shorthand for HA, or like step size times our eigenvalue thing. So yeah, so this is all the things we just did. If you have the Butcher-Tableau, you can just write it as this equation and check this. And you can plot this thing. So if we had a more, like if we wanted to do this for like RK4 or whatever, I wouldn't go through this exercise. I would plug in the Butcher-Tableau for the RK4 here, and then like plot level curves of this or something, so we could visualize the stability region for it. We could do. Okay. Any questions about any of this stuff? Yeah.
I'm curious, like, is there any issue extending this to a nonlinear system, right? Like we're analyzing all of this. Like,
yeah, this linear test problem, right? So this is like, what this really is the linear stability story that we've been talking about, right? So this tells you like this kind of, like epsilon ball type stability stuff in some neighborhood, right, of a equilibrium of a nonlinear system, right, et cetera, et cetera. So if this is stable, it is stable. If this is unstable, or if this comes out exactly 0, right, that's kind of a case where it's iffy. If it's stable, it's stable. If it's unstable, it's unstable. Because this is a linearized, first order result, the place it breaks down is when the linearized term is 0, in which case the nonlinear terms start to matter, right, like we said before. So what you can do then is now you have to start thinking about Lyapunov ideas. And you can write the discrete time Lyapunov stuff, and you can write the continuous time Lyapunov stuff. So what you could basically do is, if you had a nice Lyapunov function for the continuous system, you could basically write it down in continuous time and then plug it into the integrator and check the same Lyapunov function in discrete time on the discretized system, and like see if they give you the same stability properties. But yeah, basically, as with many things in life, nonlinear stuff is hard, and linear stuff is the stuff we know how to solve. So you can get really far with linear stuff in terms of, for stability analysis stuff, the linear stuff can take you really far. And we generally use it, and it's pretty powerful. It breaks down when the linear term is 0, right? When the linearization comes out to 0, then you're like, oh, well, then the next term in the Taylor series is the one that's going to dominate, right? And then you got to look at that.
So what about for like a periodic, like an orbit or something?
Yeah. So this is super fun. We should talk about this. Well, maybe this is a next time thing. So basically, you can compute time varying linearizations about periodic orbits. So if you want to study, there's different objects you can think about studying the stability of. So far we basically just talked about equilibrium points. So I can say, okay, if I have an equilibrium point, I'm going to stay still there. I can perturb a little bit off that and see what happens. You can do almost the same thing for a periodic orbit. So if I have a periodic orbit, what I can do is compute a time varying linearization around the orbit, and I can study. Okay, we should write this down and talk about this in like a more legit way. But if you want the quick and dirty version, I can imagine computing this linearization. Like basically, I can compute the Jacobian as a function of time around the whole thing, right? I can then take that and integrate it around an orbit, right? And that's called, there's a couple names for this. You might have heard the word state transition matrix. You may have also heard, maybe not, the real name for that on a periodic orbit is a thing called the monodromy matrix. So it's the one period linearization map. So it's basically saying if I integrate the linearization all the way around, so it's saying if I were to perturb my initial condition on the orbit here, and then like let it roll for a whole orbit and come back to the same spot, what would it look like, right? Okay, so now you're basically, you have a discrete time map now, right? That's just one orbit. And now you can use the discrete time stability tools on that periodic orbit, right? So does that make sense? So now basically what I say is if I perturb and let it go for a full orbit, it comes back to the same spot. Is that mapping a contraction? Now it's stable. If it's not a contraction, then so now you can say the periodic orbit is stable or unstable. Does that make sense? So basically all these, we bootstrap on these equilibrium results in all these other cases by basically figuring out a way to like, you know, make them look like the discrete time like case, right? So you can do that for periodic orbits, actually quite nice. And there's a very nice theory. So you can do what I just described. There's a whole theory in continuous time, also called Floquet analysis, you may have heard of. But the thing I just described is pretty much what you do. And the discrete time version is much simpler and easier to deal with. So that you can also do it for trajectories that aren't periodic, where you basically linearize along the trajectory. And you can check basically the integrated mapping. So there it's called the state transition matrix, right? So if you have like some initial time and some final time, and you have a tracking problem along a trajectory, you can say, okay, small perturbations here, how do they result in small perturbations over here at some future time? And you can check stability of that mapping and whatever, and see if it's contraction.
That kind of check the stability versus like purely imaginary.
Yeah, so I mean, if I had, say, this is all subtle. So if you care about the integrator, not the continuous system, then what you would, this gets tricky. So basically, you can write down the continuous time equations for like the state transition matrix, like 5t, which is just the integral of the Jacobian around this orbit thing. You can write that down as an ODE and you can integrate it, right? Using some integrator. So you could do that. And then you could also check, like if you say had a way of integrating that to very high order that you trusted, now you'd have that and call that, you know, ground truth or whatever. You could then go take your integrator and compute the discrete time version of it, right? Just through like the RK steps or whatever as a function of step size and compare those. Could do that. There's things you could do, but I think, again, on a nonlinear system where you have this periodic orbit thing, the issue is you don't have any ground truth, right? Like you'd have to have some way of integrating that you really trusted to get a ground truth result to then compare against to really know if it's stable. But generally speaking, we use like an adaptive Runge-Kutta thing or something that's pretty good with error control and just trust the integrator. And then you can do all this stuff. And like, usually we're not studying the properties of the integrator, we're studying the properties of the actual system. And we're just trusting that the integrator works, right? And what I'm trying to show you here is that you can't always trust the integrators. So you always want to take it with a grain of salt. And like the things to do are to check like momentum and energy conservation and stuff like that. And like do a bunch of sanity checking. Also a really good thing to do is check known solutions, right? So check for qualitative behaviors that like should be there, where you know what the answer should look like that's kind of what you want to do, right? And do a bunch of that, and then like eventually you'll develop some trust in the simulation, and then you can maybe then like actually look at some of this other stuff. And I got off on a tangent. So the last thing to say here, so there's, I think this is pretty much the end of our discussion on like these kind of Runge-Kutta methods and like simulation stuff that you should really know about. So if you want to look up more of this stuff, if you ever are in a situation where you need to care about Runge-Kutta methods and like some of the more subtle, stuff that's sort of, there is basically a ODE Bible. It's this book by I'm probably going to say it's Heirer and Norset. It's one of these big, scary German yellow books. And it's called, unsurprisingly, Solving Ordinary Differential Equations. This is actually a really great book. It's actually a 3-volume like masterwork. It's insane. It's 3 volumes written over 20 years. Like some of them are in their second editions now, but it actually, it's super readable. It's like very well written and really nice. Actually, you can just kind of, it's casual, casual bedtime reading. But they've got like stuff on just ODE theory in general and like, existence and uniqueness of solutions and like really just like super intuitively well written. And then they go into like all the numerical methods, all this Runge-Kutta stuff that we talked about, and then all the more advanced, all the adaptive step stuff, all the fancy versions of these things. They talk about geometric stuff, like things that preserve invariance, like all that kind of stuff. It goes really deep. It's actually quite nice and readable. So if there's anything you ever need to know about ODEs, if it's not in that book, I'd be really, if it's not in that book, it's probably just like unknown to science. Like there's like 1,000 pages of, everything ever about ODEs in that. Cool. So yeah, it's great. Check it out. Couple volumes. The first volume has all the stock stuff. The second volume goes into like, actually, I think volume 2 is stiff equations. And then I think volume 3 has like geometric methods, which is all these like crazy, Hamiltonian, blah, 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 like preserve all the invariance kind of things, which I think we'll actually get to in this class a little bit of. Okay, so let's do some code. Back to our friend, the pendulum again. So here's our pendulum with some damping now, like what I threw in there last time. Oh, I messed that up last time too. It didn't matter. Okay, so we're just gonna like have all these explicit midpoint, terrible. RK4, this is the classic RK4 that is on Wikipedia and everywhere. Implicit Euler that we talked about. So we got the Newton step in there to solve it. Implicit midpoint, same story. And then these just simulate for n steps for all these. Let's do so this is 10 seconds at 10 hertz. And we're just going to do them all and plot them. We can animate it, although it's not very exciting. And we all know what's going to happen, right? Pendulum damps out, cool. You got to do it, right? Okay, so here's kind of the interesting bit. So here's all these solutions stacked up, and you can see they all look pretty similar, except for the implicit Euler, which is has a lot of extra damping, right? Adds damping, as we saw from the theory, right? So not a surprise that it should do that. What can we do now? Let's jack up the damping some more. Start to see what happens. So this is kind of getting at this like whole point that like, so these all do okay. So now it's over damped, right? It's just gonna like fall down. If I keep jacking this up, what you'll find is eventually like, again, yeah, like there's nothing in terms of like sample rate and stuff, right? There's nothing happening here that's faster than 10 hertz, right? In terms of Nyquist or whatever, it's all super slow. So like 10 hertz should be plenty from like that kind of perspective. Let's see. I think this is where it actually breaks now. So yeah, now things have started to blow up. We can go now and they'll pick out individual ones and look. So did RK4 survive? Let's find that out. That might be. Let's see if RK4 did okay. It may have. So no, RK4 blew up. Sad. But RK4 will do a little better than the other explicit ones. So let's see, implicit Euler, implicit midpoint. These are both probably fine. Yeah, so both of these are fine. And according to the theory, right, if I add damping, I'm just pushing everything farther into left half plane. Both of these are astable, so they're fine forever. So I can jack this damping up as high as I want, and they'll do just fine. But the explicit ones, both RK4, even a good explicit method, right? So if I took this and fed it to like a fancy adaptive Runge-Kutta method and kept jacking the damping up, what would happen is, in order to keep things in the stability region, it's going to keep having to shrink H, right? So if I fed this to like ODE 45 right now, where this sunset, it's going to end up shrinking the steps out of when we sit here like 20 minutes for it to integrate for 10 seconds. So that's what's going to happen, right? So if you're in a situation like that, using something like ODE 45, probably you want to switch to an implicit Runge-Kutta method. And it turns out, while they're more expensive, they will just absolutely win in a situation like this. And you don't really have to care too much about the step size. You can just use a fixed step one, and it'll do just fine. Okay, I think that's all there is to say about that. Anybody have anything else you want to try?
How much more expensive?
Yeah, so there's lots, so it depends. So basically, like, you can see what's going on here, right? So this is RK4, so I'm calling F 4 times, and then I'm just like, weighting those, right? That's fine. So 4 F evaluations. Let's go look at, say, like implicit midpoint, for example, or implicit Euler, one of these. So this guy, I'm evaluating F here, that's ones. Then I have this loop, and generally it will take 3 or 4 Newton steps to converge. So in so this basically, right now, as this is written, I'm evaluating F probably 3 or 4 times and the Jacobian 3 or 4 times. So the Jacobian evaluation is more expensive than F itself, right? Blah, blah, blah. And I'm solving a linear system. So this is, as written, this is probably like 10x more expensive because of the Jacobian call and whatever, but it doesn't have to be. So I'm using like full up Newton here. You don't have to do that. You can use a quasi-Newton method, like Broyden's method, right? Where you're like using gradient evaluations and blah, blah, you don't have to explicitly form a Jacobian to make that more efficient. You can also, there's other tricks you can play. So if you actually know what the system is, and you know those things about it. So a naive thing you might think about doing with one of these is you might say, oh, well, to get a decent approximation for like xk plus 1, why don't I take a like explicit step and use that as my initial guess in this Newton solver? I think someone suggested last time or 2 times ago. The reason you don't do that is on a stiff system like this, what's going to happen if I take an explicit Euler step? Euler, it's going to blow up, right? And then I've just screwed myself, and then my Newton solver won't converge, and everything's just bad and blows up. So that's bad. You don't want to do that. But you can imagine on like more benign problems that are not stiff, I can actually do a pretty good job of that. I can take like some explicit step that gets me an approximate solution, and then I can use that to like warm start the implicit thing. So that's actually common to do specifically in orbit mechanics. So in orbit mechanics, things are really smooth and like there's no damping. And in orbit mechanics, we tend to like to use really high order integrators because they let us take really big steps and they're more efficient actually on a problem like that. So you'll see people use like 7, 8, even higher order integrators. And there, it turns out, because things are benign, you can get away with this like warm start trick. And it turns out you can actually write the implicit integrator step as a fixed point iteration. So you basically like warm start it with an explicit step and then do like a fixed point iteration a few times to dial it in. And you don't have to take a Newton step like this, and you don't have to explicitly compute the Jacobian and stuff. And then it turns out it's very efficient. So it depends, but that fixed point iteration only converges on like stable, nice dynamic problems, right? Like for really gnarly problems, stiff problems, you have to do this like Newton type thing, in which case it's just more expensive, right? But it lets you take big steps. So because of the ability to take the big steps, like on a problem that's stiff, this is absolutely going to win, right? Like I can take 10 Hz steps on this just fine. Whereas with an explicit Runge-Kutta method with adaptive step sizes, I might have to take 5 kilohertz steps to not blow up. So in that case, this might be 10x more expensive per step, but I can take, 1000x bigger steps. So it's 100x more efficient, right? So that's a very common move. So that's kind of the story. They are more expensive, maybe by an order of magnitude per step, but they let you take big steps and not be, having to do crazy time step adaptation kind of things. And they also do other nice things. They preserve like the structure of the solution in a bunch of qualitative ways. Okay. Anything else? Should we try anything else? No. Euler, never the best. No Euler is the best. The Euler thing here, right? This was kind of the Euler one, implicit Euler is super like over damped and sort of does all this artificial energy dissipation stuff, right? Yeah, this stupid thing. Okay, so remember, here's the implicit Euler, right? This is artificially stabilizing all these things over here with like additional damping, right? And when I went and sort of simulated this thing with like a reasonable damping constant, not an insane amount of damping, right? If I go and do this, And I plot them all again.
Stabilize and then stabilize.
Yes,
Like,
yeah,
you're-
that's exactly what that plot says. Yeah. Yes. Yeah, actually, we should do that. So yeah, this thing, if I put the pendulum in the unstable upright equilibrium and I dial in the time step just right, it'll artificially stabilize the unstable equilibrium. That's what that plot says, right? That's what that, we could do that. Let's actually figure that out. So yeah, basically what I can do is I can take the unstable pendulum and for sufficiently sort of like, what would it be? Like, basically if I can get it in here somewhere, right? I can stabilize that upright equilibrium. We can probably make this happen. Let's try.
So you just need a really small step size.
Let's see. Yeah, or really big, right?
Yeah.
Or I can push it all the way over here, right? I think we can make this happen. Try. Let's try. Yeah, I think if I make this super big, I mean, not even super big. And then what do we want? We want it at right there. Let's try and see what happens. Oh yeah, I need to perturb some amount, right? So let's try. So they're all blowing up and doing the right thing. What do I need to do? Maybe jack this up some more. Oh yeah, that was going to happen anyway, though. It's not interesting. What am I trying to do here? We'll get rid of this. Yeah, okay. So yeah, I'd have to play around with this a bit, but yes, that will happen. We basically have to get it into that region of the plane. And if I sat here and did some math by hand, I could figure out the numbers just right to make that happen. But yeah, you can do it. This is enough damping probably. I make the time set really tiny. Anyway, yeah, you get the idea. So now they look pretty decent. I think I have to both do big. I think I want this to be big and the damping to be big. Yeah, anyway, you can try this yourself. The code will be on GitHub. But yeah, that's exactly what that says. Yeah. Okay. Anybody have anything else fun to try? This is a fun thing to try. Should totally do this. That's all I got. Yeah. So next time we're going to start talking about rigid body dynamics and like kind of multi-body dynamics. Yeah. A little more analytic stuff. Then we'll get back to this stuff with some weird specialized methods for Lie groups and stuff like that. Okay. Catch you later.